This talk is very broad. It touches on all sorts of, on basically almost all of the research I'm doing at the moment in my research group. And so, of course, everything I talk about will be quite shallow. I'm only giving the broad ideas. And the idea, of course, would have been, I would have been in Melbourne and you could talk to me during a week if you're interested in something specific, things being as they are. This is not the case. What I can offer you, of course, I mean, write me an email. If any of what I'm talking about here catches your interest, please write me an email. Let's get in touch and keep the ball rolling until better times eventually come rolling along. Okay, with this, I'm gonna go into it. So the core of my research is AI planning. As you probably know, I'm not completely aware how broad this audience here is. In any case, don't worry, I'm gonna give a brief introduction to that too. So let's start with that. And before I say anything else, these days, being an AI person, I kind of feel the need to clarify first what I actually mean with the term. So I grew up in the days of what has now been refashioned, actually good old-fashioned AI. It used to be something else when I grew up, but now I'm part of it. And that's okay. As you all know, in recent days, these guys here have made the headlines. And like many other people with my background, what I'm advocating for is this. So the integration of neural and symbolic methods. I have many ideas along these lines. I have to also say I'm at the beginning of this enterprise. So there are many research projects that have started, some PhD students that have begun about 1 or 2 years ago, and also more recently than that. There are many interesting ideas. I think it's a very exciting area, but I can't claim that I've made a lot of leeway there yet. So like, I guess, well, the research field is in its infancy, and I want to be part of that, and I am part of that in an initial way. Good. With this out of the way, let us talk about what we mean by planning in the AI context. What you see here is a typical problem that can be phrased as what we call a classical planning problem. This basically just means that you're given a unique, fully determined initial state, like the configuration of the cards that you see on the table here. You have a goal, namely to put away all the cards in the right order in the top right corner. I mean, this is actually a card game Freestyle that you might have played back in your youth or sometime when you had the time to be bored. I haven't had that time since about 20 years, but okay. Okay, you want to reach the goal, and you have actions that you can use to transform the world state, in this case, moving around the cards according to certain rules. And what you're looking for is a sequence of actions that takes you to the goal. This is basically the simplest possible formulation of an action decision problem. It's a special case of sequential decision making. Now, of course, you're not interested in this particular card game. What you're interested in is a very generic methodology that can solve any such action decision problem, provided it's specified in a given fixed input language. This here is the simplest possible definition of the input language. Let's not even consider the definition. Let's look at the example. We assume that the world state is specified in terms of a set of state variables. In the example here, we have a variable giving the position of the truck and one variable for the position of each package. Those variables each have a finite domain of possible values, a finite range of possible values. And the actions, and this is important, are specified in terms of conditions over those state variables. So for example, the loading action, loading package I at position X, has a precondition. The precondition says the truck has to be at position X and package I also has to be at position X. So in general, the precondition is just a set of required variable values. And the effect then is a specification of how variable values change. So this particular action says that the package I is now no longer at X, but instead in the truck. Okay, I hope this is intuitive. The initial state is then just a variable assignment. In this case, it happens to be the one I picked up here. And the goal is also a set of variable values that we require to be true at the end of our action sequence. Good, and because this is obviously a simple toy example used for illustration, let me briefly point out that we can apply this kind of model. And because it's so generic, we can apply it in many different contexts. I spent some time at SAP Research, worked on applying this in the context of business process management as a method to generate business processes, or rather business process templates, because you can't expect the automatically synthesized process to be final. You still have to edit it, but it gives you a kickstart, basically. Then completely different construction side, you can also use the very same framework to generate natural language. That's how generic it is, right? You can do it in SAP, you can do it in language generation. In particular, if you assume that the problem of generating a sentence is specified in terms of a grammar, then that grammar becomes your planning model. And the goal is then the intended semantics that you want the sentence to express. And then it again becomes a push button operation. Now, I don't know if there are some language people in here, natural language processing people. I hope there are. And if there are, you probably thought right now, well, this is a very old-fashioned approach to natural language generation. Neural networks these days achieve much better performance at natural surface level generation. That is true. I still think, and the NLP colleagues here at my university agree with me, that planning methodology is still relevant, because the problem of neural methods is you cannot control the semantics, right? You actually have no control over what they're actually saying. I mean, it sounds good, but does it actually say the right thing? And I'm going to get back to this later, because that's something I'm also currently working on here in a collaborative project. Another application, not by myself, by colleagues in California, like Xerox. I think I'm going to go over this quickly. I mean, it's basically, if you want to control a printing machine, then usually you would design a single control program. However, if you want to write a single control program that can control an arbitrary machine picked from a very large possible design space, then you actually need AI techniques to do this. And this is also something you can do based on planning models. So this is the end of my little introduction to the area. This here is the big picture. We have a strong emphasis on generality. So this is basically the GoFi background, right? Which in practice, in research, everyday life, essentially means we're tackling very complex decision problems. And so one core focus in the area has always been just computational complexity and how to deal with it in a practical way. So this is what I mean by algorithm design. This is also my own background. I'm going to give basically some snapshots from this background in the following minutes. More recently, I've taken up research on explainable and safe AI, and I'm going to talk about this on the two major topics I'm currently working on. And then I've also done work on applications. Now, with applications here, I really have to say, I mean, application areas. So I'm collaborating with colleagues in natural language processing and also in security. And I do have that some colleagues from Melbourne from those areas are here, but obviously I don't know. And if you're working in any of those areas, many of the things I'm going to be talking about will seem familiar to you to a certain degree. So AI planning is firmly placed in the landscape of computer science with many intense links to other areas. Good. Algorithm design. So here our objective is essentially really just somebody throws a planning task at us. So somebody tells us what the initial state, the goal, and the actions are, and we're supposed to come up with a plan. The problem is in general at least piece-based complete. How do we design algorithms to solve this kind of problem effectively so that actually the user can get an answer in less than a million years? One very successful approach to doing this is heuristic search. I'm not sure if I can assume that you all are familiar with this, so let me very briefly take you through it. It's super simple. The principle is super simple. You start at the initial state, you just apply actions in a forward search. You just work away forwards from the initial state and until you've reached the goal. The problem is so essentially you're just looking for a path in a graph, but the graph is way too big to build completely. So you want to focus on the relevant part of the graph. That's the idea in heuristic search. You do this by defining yourself a function h, the heuristic function that maps states to numbers. Those numbers are supposed to give you an estimate of the distance to the goal. Then you just prefer states that seem to be closer to the goal. So that's a very simple principle that, of course, relates very strongly to things like branch and bound and operations research. So this H here in other areas is just called the lower bound. In AI planning, it can also be the lower bound if you want to do optimal planning, but you also a lot of the time work with heuristic functions that do not give a bounding guarantee, because often it's actually too hard to obtain such a guarantee, or there's a lot more you can do if you drop that guarantee. And then it's not about optimal planning, it's just about finding some path, but sometimes you have to, trade optimality for effectiveness. Okay, one key question in planning, since everything is supposed to be automatic, remember GoFi, right? We don't have an engineer who programs that heuristic function H. Instead, we want to automatically create that heuristic function just starting from the declarative problem description. And if you want to do this, of course, you got a huge research problem, and that research problem has been, well, a main trend in the AI planning community since the last 20 years. I've been part of the trend, as you can see up here. The underlying principle of all those heuristic functions is quite simple. It's just a textbook principle of relaxation. Probably you are familiar with the principle. In any case, for example, if you want to find a route from Saarbrücken to Edinburgh or to Melbourne from that matter, one way you can devise a heuristic function is by relaxing the problem. I could, for example, ignore the fact that there are some oceans between here and Melbourne. And then the distance to Melbourne, like the travel cost, is just a straight line distance. And this is a lower bound approximation that I arrived at by first defining a relaxation and over approximation of the problem. So I assume you've seen this kind of thing before. Okay, now in planning, of course, the question is, how do you relax a general problem description? And that also depends, of course, a lot on the language. One principle we have looked at a lot, and this is really basically in my past, so I'm going to do this very quickly only, is the lead relaxation. The basic principle behind this is this. So in the real world, if you buy something, then you give somebody else the money. Okay, so you get something, but in return, you lose something, namely the money. In the delete relaxation, we relax the world by assuming that these things don't happen. You don't lose anything. So you buy the car, the other guy gets the money, you get the car, but you also get to keep the money. This, of course, very convenient. It simplifies the world quite a bit, right? It's enough to earn a single salary once, and then you can live on it forever after. That's convenient. Remember, this is just taking place inside the heuristic function. And also, as I've just illustrated, this is actually a weakness of this heuristic. It ignores the fact that resources are being consumed, right? And this is bad. It's a big source of information loss. And so people have looked for a long time at how to actually reduce that information loss. And in my research group, we framed this in the systematic way of partial lead relaxation, which are powerful relaxation methods that have some sort of interpolation parameter that allows you to trade off in a fine-grained manner between the lead relaxation, which is encoded in the H+ heuristic function, and the actual cost of solving your planning problem, which is encoded in the so-called H* function. Okay, this has been a large focus of my group in the past decade, but I'm going to just leave it at that here. I've also worked on analyzing the properties of heuristic functions, just to mention that I'm not just somebody who wants to engineer systems, I'm also interested in understanding them. And in the particular case of heuristic function quality in planning, I was able to obtain very significant results that I'm not going to explain here in the interest of time and in the interest of getting to some topics I'm actually working on now with my current PhD students. By the way, I haven't got a slide acknowledging this explicitly, but of course, all of the things I'm going to talk about now are to 90% done by my PhD students. Okay, this is something I've been doing since a while, which I'm quite excited about. It's called star topology decomposition. Let me illustrate by first ignoring the fact that we're in a planning context. What you see here is a certain underlying structure of the simple planning task I showed you before. Intuitively, the packages depend on the truck, but not vice versa. That's why those edges have a direction. This is a dependency between the objects in my planning task. Furthermore, and more importantly, each package individually depends on the truck, but there are no direct dependencies between the packages, right? One package doesn't care about another package at all, right? The only reason they interact with each other at all is the truck. They all depend on the same resource. Now, if this was a Bayesian network, then we would certainly conceive the idea to just take out the center, right? Or constraint satisfaction problem, right? You instantiate the center, you break the conditional dependencies, the whole thing falls apart. Okay, this is very simple, and it's even a very simple special case, so we can easily apply this sort of methodology. But remember, it is not a Bayesian network. It is a structural property of a planning task description that actually defines an exponentially large state space in which you want to find a plan. So what does it mean to instantiate a center? If you ask the question this way, you probably won't come up with the answer. And we didn't come up with the answer this way. It's just a way I find convenient to actually present the final outcome. And the final outcome is this. One way to give meaning to the term instantiate the center in this context is to fix the transition path, but only for the center component. The center component here is just a single state variable. In general, it can be a set of state variables that we then basically fix as one component in our planning task. So we fix the transition path for the components separately. And then given such a fixed path, so now we're back sort of in the terminology of Bayesian networks. So given a fixed instantiation of the center, we don't have to anymore enumerate combinations for states of the leaf components. So given a center path for the component, we can search over the leaf components separately and thereby avoid the exponential explosion over the leaf components. I'm just gonna mute somebody who made a noise right now, just to make sure there are no more interferences. Okay, so this is the basic idea. I'm not gonna give you any more technical detail. If you're interested, like I said, drop me an email. Let me take you to the results directly, which are quite impressive. So if you just go to the bottom line here, what you see is a comparison to state-of-the-art partial order reduction methods, because at the end of the day, when you think about it, this is a way of reducing partial order redundancies, right? But in a very particular way, focused on this star topology. And this turns out to be very effective. So compared to unfolding and strong stubborn sets, we beat them like by a factor of more than 2 in coverage. And of course, this is exponential scaling. So a factor of more than 2 in solved problems is quite extraordinary. You can also see it in more fine-grained level on the right-hand side. For example, in this domain, we achieve a reduction by about a factor of more than 1 million. And this is just on the commonly solved examples. And I should also say this is for state space exhaustion. So representing the entire state space, which is not what planning people are usually interested in. And I'm going to get back to that in a moment. There's also a weakness on this slide, which is not immediately apparent if you're not working in planning. The weakness consists in the fact that I'm only showing you 20 domains here or 16 or something. And this is not the whole set of planning benchmarks out there. You have a common set of benchmarks which actually contains 70 domains. Why do I show just 20? Well, those happen to be the 20 where there is actually a pronounced star topology. And of course, this whole technology here only makes sense and can only achieve something if you actually have that star topology. This is not the case in every problem. Now, given this, A, we need a star topology. B, our strongest suit is actually state space exhaustion. Well, what does this take us to? Well, it actually takes us away from planning and into the world of model checking, because A, in model checking, you have lots of star topologies, right? It's a classic system design principle. B, state space exhaustions is exactly what verification people are interested in, right? They want to enumerate all possible behaviors of the system. So this is what you're looking at. We are doing this since a while. We have obtained promising results, getting us the best paper award at the SPIN conference. You're basically beating SPIN and state-of-the-art partial order reduction in the SPIN system on a couple of standard toy benchmarks. Now, of course, this is just the beginning. Currently, we're working on liveness properties. There's a submission under review at the CAF conference right now. And we want to do a more realistic case studies on weak memory models. So all of this is quite work intensive, I have to say, but we are getting ahead. And it's something I definitely want to emphasize on. Okay, good. Next algorithmic topic, I think I'm going to do this very quickly only because I've already talked for a while. Conflict-based learning is something you're aware of from constraint satisfaction. Certainly, Google gives about 3 million results. This has been very underdeveloped in state space search. So in the past, basically, people just knew how to do duplicate checking. I mean, this is, of course, all over the place, but it doesn't generalize, right? You want to generalize from the previous mistakes. You don't want to just exclude the exact mistakes you made before. You want to learn something from them that generalizes to avoid similar mistakes. Now, duplicate checking doesn't do that for you. In the 80s already, people have tried to learn pruning rules, but then they couldn't guarantee that they are sound. So they generalized, but you cannot guarantee that what they prune is actually a bad thing. So you lose completeness. And in our recent work with my PhD student, we found ways of actually achieving both soundness and generalization. I'm going to skip over how we actually did that. The results are very good. Here you can again see the difference without learning versus with learning in terms of number of solved problems. So it's again very large differences. Here I should say that this is limited to planning situations where you want to tackle limited resources. So if you have a planning problem where thinking carefully about how you assign your resources is the core problem, this is a good idea. Otherwise, maybe not so much. Okay, good. Finally, And this is now getting again to the things I'm doing right now. So this is more present time, neural networks. I'm intensively working on applying neural networks in this setting. I mean, you all know AlphaGo and AlphaZero, amazing results in playing board games in the planning community. I mean, we are kind of all thinking, well, I mean, if this works in Go, it just has to work in planning too. It turns out to be surprisingly maybe difficult to actually achieve this kind of result in our community, but they're working on it. So what you see here is one particular setup where we're using reinforcement learning to learn a heuristic function. The blue and the red line, I mean, this is coverage, so number of solved tasks over the time limit, over runtime you give it. The red line is the state-of-the-art, canonical state-of-the-art model-based system, so traditional system. And as you can see, the blue line is higher than the green line, so we're beating the state-of-the-art here, actually quite substantially. And same happens to the red line. Blue and red, the difference is not so important to us here. So what this figure shows is we can beat the model-based state-of-the-art based on reinforcement learning in the planning community. However, this here is just one benchmark domain, and it's the only benchmark domain where this actually happens for us. So in all other benchmark domains, the model-based state-of-the-art beats us quite substantially. So we're still suffering from a lot of brittleness in performance of those methods. And part of the reason for this is, well, planning is not a board game, right? Our input language is not a picture. It's a logic-based model of states and their transitions. So it's not that easy and not that natural to capture with existing neural network methods. The most intuitive solution, of course, is graph convolution, and the planning community is looking at this. We haven't really quite found the key. So what is the best graph? I mean, there are many ways you can define graphs that somewhat describe aspects of a planning task. Which are the right graphs to use? It's very unclear at this time. Also, we want much stronger generalization. We don't want to play just one board game, even if it's Go or chess. We want to solve arbitrary problems, and we want to ideally generalize over goals and over instance size. So I'm looking into all these things. I don't yet have many results that I can present to you today. It's basically the ongoing research agenda and up to the next 5 or 10 years, I would assume. But let me take some time also to talk about other things than just algorithm design. So now we're not talking about just, you know, solving a hard problem as best we can. Now we're talking about actually, okay, assuming I can actually solve the problem, how do I explain what I did to the user who might be asking questions? And how can I assert safety of the system if machine learning is involved? And these are basically two separate trends, right? It's not the same thing. One, explaining things is one thing, asserting safety is another thing. I'm going to talk about those two separate research questions, basically two separate major research strands in my research group at this time. Okay, plan space explanation I'm doing in this context. This was originally conceived by David Smith at NASA. The fact basically being that, I mean, I can just as easily explain it on the next figure, actually. So the usual assumption in the planning community and in the classical AI planning world is basically the user poses to you a task, right? The user defines the planning task in the input language. Then you start the system, you push a button, the system spits out a plan, and then the user is supposed to just execute that plan, right? So as the system, after we produce the plan, the game is over for us. There's nothing more to do, and the user is just supposed to be happy. A problem is users usually aren't just happy that easily. So if you throw the plan at those guys here in the ground control center, they're not just gonna take your plan and execute it on the 1 billion device out there on Mars, right? They're gonna want to gain some trust in the plan, and that is actually a good plan, right? There are some high stakes here, and they're gonna want to understand. For example, they might want to understand, okay, so thanks for the plan, but why this plan? Why not, you know, what is good about this plan? Why are you suggesting this plan in particular? So this is a question that users are likely to ask, or that's certainly one useful question to be asking in such a process, where you basically want to iterate over the plan until you feel confident that you have arrived at a good plan. Now, framing the question in this way, of course, it's impossible to answer, because what does the user actually mean with that question, right? If you want to operationalize this and define some AI technology that can do something about it, you need to have a more specific question, or at least that's one way of simplifying the problem for you, right, as an AI researcher. And so what you're doing is you're putting the user into a core set, and we're allowing them only to to ask questions of this kind. So we're fixing a set of what you call plan properties. These are just Boolean properties of plans that the user is interested in. You could also call them soft preferences. So the user has a number of things that they are in principle interested, so desirable things that the plan could achieve. And now the user can ask, okay, why does this plan not have that property A here that I'm interested in? And then given this frame, you could answer it in this way. Well, because if we do give you A, then we can't give you B. Okay. And in this way, the technology that we're doing basically elucidates the trade-offs between the preferences to the user. One slide on formalization. We're formalizing all this in terms of soft goals. Essentially, those soft goals can encode arbitrary Boolean functions of the plan. In our implementation, those are LTL formulas, so linear temporal logic, which is just the canonical language to be using in the on the AI side. And it's fairly general, so it's fairly expressive. I think I'm gonna skip over this definition. What we're basically just saying is that A entails B in plan space, in the sense that every plan that satisfies A also satisfies B. Notice that this is not standard attainment between LTL formulas, right? Because it's restricted to plan space. So basically, plan space becomes the knowledge space that forms the background to our entailment relations that you're interested in. Okay. In terms of computational performance, I'm not going to explain all the bars and dots on this slide. Let me just go to the total and point out that the blue dot here is the number of solved tasks for oversubscription planning, which is the most closely related standard planning problem, and which is actually easier than our problem. Our problem is to pre-compute offline the answers to all possible questions. If we do that, if we solve that computational problem, we solve over subscription planning as a side effect. And nevertheless, as part of our research, we were actually able to obtain better performance in solving this more complex problem. So we actually improved the state of the art in over subscription planning as a side effect, which is kind of funny. But the main message here really just is, this is not as infeasible as you would think. So pre-computing all possible answers to all possible questions of this kind here is actually feasible, at least compared to things that the planning community has been doing all along. More importantly, perhaps, reviewers have, of course, been pushing us towards evaluating this from the user side. So how useful are those answers, this question answering paradigm? How useful is it actually to human users? It's been a lot of work getting this to run, but we're finally there. We're running a user study right now as we speak. A PhD student is doing this on a prolific platform. These are preliminary results. They aren't published anywhere yet. I just wanted to include them. I mean, I actually saw those results the first time last Friday. Okay, but what you see here is user performance over time. So there are two test groups, like Q plus has our question answering facility, Q minus doesn't. What you see over time is the plan utility the users managed to achieve as a function of time. Now, what you see here is that in the beginning, the Q minus users achieve better utility than the Q plus users. And if you look more closely at the data, what you see is that basically the Q minus users in the beginning, they basically try around more. They try more different plans because there's not much they can do. The problem is too complex to just understand it in your head right there. And so they try around a bit. And if you just try around a bit in this particular planning task, you can get some utility fairly quickly. Whereas the Q plus users who have the question answer tool proceed more slowly, basically more carefully. I have this tool here. What information does it give me? What can I do with that? So initially proceed more slowly, but then eventually you see it pays off. So eventually the Q minus curve flattens out because they're not able to get more utility, having difficulty to understand all the implications, all the dependencies between the properties, whereas with the tool, you're actually able to understand this more deeply and finally obtain better plans. So this is preliminary. It's just one of the 3 studies we're running. So I'm going to have to see how this pans out, but I find it a very interesting first result. And so I wanted to share it with you. Okay, I find this a super exciting research line, and I expect to be working intensively on it for the next 5 to 10 years. One interesting challenge is deeper why questions. So this, your favorite NASA engineer might not be happy with the answer, why can I not take a photo of the crater? Well, because then you could, but then you can't take a photo of the lake. Your NASA engineer might actually ask why. Okay, so why do you think this is the case? So maybe the NASA engineer doesn't actually trust the model, the planning model, or maybe the NASA engineer thinks I could change some parameter somewhere else and get a better outcome. And so how to define what possible answers to such deeper questions are is an interesting challenge in itself. And once we address that challenge, of course, there's all the computational problems and all that follows. But let me proceed to the next research line, which is also quite interesting. I think so people out there, of course, are more and more just learning neural networks to take action decisions, right? So why do you need planning methodology at all, right? Just offline, learn a neural network action policy that maps states to actions, and then online, when you're acting in the world, whenever you need to take an action, just call a neural network on the current state. It will give you an action, execute that action, done. Now, this is potentially very performant, but of course also potentially very dangerous and disconcerting, because how do you actually gain trust that this policy, that this neural network that you've learned has learned something useful, that it will be safe and adequate from all sorts of other considerations, including also ethical ones. I'm not considering ethics right now. I know that it's a potentially important topic in Melbourne. That's why I'm briefly mentioning it. Of course, at this point here, there's a big possible link up to ethics and actually all other forms of social science, non-informatic sciences, I should probably say. But I'm not considering this so far. What I'm considering so far is basically, on the one hand, analysis and safeguarding, and on the other hand, explainability. Safeguarding you can do by looking ahead, not just doing what the policy does, but looking ahead a bit. So basically finite horizon, look ahead. I'm also working intensively on debugging. So basically finding, just see if you can automatically find test states on which the policy actually performs bad. So for example, crashes, even though the state is not necessarily a crash. I'm also working on verification. Currently I have a PhD student working on a predicate abstraction paradigm where we can eventually actually prove that the policy is safe. So you have a large state space, you have a neural network acting in that state space. We're working on methods that can formally prove that there are no unsafe behaviors induced by the policy. Just to know the complexity, this is so complex, it's almost ridiculous. It combines the complexity of the state space explosion with the complexity of analyzing neural networks. Nevertheless, we have a first paper ready for submission, and it turns out it's not actually that infeasible. It's not as infeasible as you might think. But I'm going to leave this for future papers to nail down. Explainability. Okay, let me just go into the things I'm currently doing. So these are things I've already published papers on. Statistical model checking is a very pragmatic approach to verifying a neural network action policy. Imagine you have a policy acting in an MVP. And whenever you fix a start state, you can very easily gain confidence in the policy's behavior simply by statistics over sample runs. And deep statistical model checking is just a fancy word for saying that. We've tested this in the racetrack benchmark that you might be familiar with. Basically, you have to get from a start line to a finish line. These are 3 different maps where you can do this kind of thing. What I'm showing you here are heat maps where we start the policy from each cell in the map. And then the color coding basically tells you how safe the policy is. So what's the probability of crashing into a wall? If it's green, the probability is low. If it's red, the probability is high. And in this way, of course, you can get a very quick insight into where the policy is unsafe. In particular, on this ring-shaped map, we see that the policy is very unsafe in this region of the ring. Now, why is this an interesting idea? Algorithmically, it's super simple. There's really nothing new here. What's interesting about it is that the neural network here is just a black box. All you have to do is call it. And so compared to other methods that are trying to prove something about the behavior of neural networks, it's just dirt cheap. And as a matter of fact, the main parameter that influences how expensive it is the variance of the policy. So the variance in the reward it manages to achieve And this variance is not necessarily higher for a learned policy than for a handmade policy. And this experiment here confirms this in a very simple setup where on the one hand, we have a neural network. On the other hand, we have a simple rule-based policy. The rule-based policy actually turns out to be harder to analyze with this method because it has a higher variance in performance. Now, of course, this is just one example and just two policies. All I'm saying is it's not necessarily harder than verifying policies that have been designed with more traditional engineering methods. I'm also collaborating with colleagues from visualization on visualizing action policies, and there's also quite a lot of exciting stuff. I was actually amazed by what those guys can do in a matter of weeks. We have the super interesting interactive hierarchical visualization of a neural network action policy in racetrack. It's pretty cool, but I don't have time to show it to you because I also want to take 5 more minutes. I mean, we started a bit late, so I guess 6 to 7 more minutes to talk about these two areas that are basically related areas from a planning general AI perspective. You can view them as applications. Of course, no offense to researchers actually working in these areas. What I'm actually doing is collaborating with colleagues to apply methods from AI planning in those areas and eventually drive to actual industrial applications where this makes sense. Okay, one thing that has actually made the industry is what I call simulated penetration testing. Penetration testing is actually the process of attacking your own network. If you're working in security, you're very familiar with this. It's a well-established technology. The simulated here could also be replaced by model-based. So if you have a model of your system, then you can basically simulate attacks in the model. I mean, it's basically just modeling and simulation, right? You model your network, you can simulate attacks, and then planning is the process of planning the attack. So it's basically a directed way of simulation, trying to find weaknesses in your network defenses. There's a company called Core Security who are actually doing this in their product. I mean, at least they did this 10 years ago. I've since lost contact. The company has developed, as it happens, in 3 markets. But in any case, this was their setup, at least back in the day. They were building this platform here, Core Impact, which had all the necessary information in order to be able to design a simulation. So all the information about software vulnerabilities and the customer's network setup and so on and so forth. Given all this information, which is very costly to maintain. I mean, this is where all the manual labor goes, right? And also this changes all the time, right? New vulnerabilities are found all the time. So they're maintaining this information, but that's what they were doing anyway. And once you have this information, you can really just define an export function to a standard AI planning language. And this export function remains constant, and the AI planning language also remains constant. So you get this for free, basically. And they can also call an off-the-shelf planner, also for free. Now, of course, it's not quite that simple. The reason why I'm talking about this here is the company eventually contacted me to give them some support in using my planning system. And they also closed the loop by implementing an execution of the plan, translating it from PDDL back into their pen testing framework so that you can actually execute the attacks the simulation found in reality. And this might sound a little fancy and dangerous. And as a matter of fact, what I'm told is that their customers don't use that functionality. Nobody likes some automatic system be attacking a network all the time. And apart from that, it could also be quite disruptive and at least generate a lot of superfluous network traffic. So that's not what they do. And also this model here is, of course, very abstract. It cannot and will not capture your network at all in all detail. This is just impossible. It's going to be abstract. So there's no guarantee that the plans work. Instead, what this is actually useful for is to point out to the security team where to look. And this is quite a useful functionality because the haystack of system defense is really a huge one and it changes all the time. And companies are usually not willing to assign lavish money to their security teams because this is not a money source, right? It's a money sink. So security teams are chronically understaffed. And so I'm totally quite thankful for having a tool that tells them to look here. And this is basically the SACE case they've been making at Core Security. At Saarland University, I'm more on the academic side. I'm collaborating with colleagues from cybersecurity here at the university. And what we've been looking at is putting the defender into the bargain in a Stackelberg setting where you have a single defender move, right? The administrators want to secure the network. and then the attacker makes the move. And so this here is about what we've phrased mitigation analysis. And it's basically a model-based way to support strategy making. So the question for the defense is, what should I change? And of course, changes have a cost. And so you always have to face a trade-off between the cost you're willing to allot to defenses and the possible benefits that you gain from that. And at the end of the day, you can view what we're doing here as a model-based way of predicting the gain that you get from allotting a certain budget to your defense. Down here, what you see is, so let us just look at this graph. What you see is, so then what you get is basically a Pareto frontier, right? So there's a trade-off between the defense cost and the probability that you will be subject to a successful attack. And what you see here is basically the outcome of analyzing a model for attacks of different coalitions of countries against Germany. Now, of course, this is completely hypothetical, right? And of course, it's all subject to the quality of the model. But you can see these curves here. If you just look at the figure very briefly here, basically see the trade-off that Germany faces if it wants to defend itself against the Five Eyes coalition, which I believe includes Australia. So it's basically Anglo-Saxon countries, Anglo-Saxon language countries, USA, UK, Australia, Canada. Forgot who is the fifth one. And what you see is basically if you're willing to spend 10 to the 8, and this is actually euros, the measurement on the x-axis is euros, then you can reduce the probability of attack to almost 0. But if you're not willing to spend quite that much money, then the probability of being attacked goes up. And now, of course, 80% of this work, I mean, my part here is the algorithmic part, 80% of this work on actually making this graph meaningful is the model acquisition, right? How do you get a model that actually reflects internet attacks in a way that is meaningful and precise enough to make this result here meaningful? And this is the work of my colleagues in cybersecurity. And of course, they are the experts there. Just to acknowledge this. Finally, I've run out of time, but to let me briefly talk about language, and I'm going to take only 2 or 3 more minutes. You've seen this slide here already. What I'm doing right now is instruction generation. And here I'm getting back to the point I made about being able to control the semantics of the language. If you're instructing somebody to build something and it's important that it's built the right way, then you cannot just let the neural network do the job of generating the instruction, right? The neural network is going to sound like a good instructor, but they have absolutely no control that it's actually giving the right instructions. And we believe, like with we, I mean myself and my collaborator, Alexander Koller, that we just need model-based methods, symbolic methods, in order to give this whole thing a direction and be able to control its semantics. We are doing this, we are investigating this in Minecraft, and the way we are achieving it there is by a combination of hierarchical planning with sentence generation, surface level sentence generation, where the two interact in a 2-level search. So all I'm going to say about this. For the future, in a more timing this in a more generic way, planning is a way of controlling the semantics. Neural networks are a way of getting the surface language. How can we combine the two? So this is really the core question here. And this is a question that could drive research for, I believe, 5 to 10 years. And one idea I have in my mind, and I'm going to give it to you right now. Maybe it's interesting to you. I mean, maybe someone on language is here. It will be interesting to you. So one idea I have in my mind is planning in Latin space, right? If all those neural encodings, those neural language models, they map the surface language, the text, into some latent space in latent state defined by the neural network. Like in an autoencoder in the middle, you get this latent state that is not interpretable to humans, but that carries a lot of meaning of the surface language. And so if we could take that latent state and actually turn it into a planning model in which we can plan, then theoretically we might be able to actually control where the neural network is going. But this is a very hypothetical idea that I just wanted to throw here, and that's going to be the last thing that I throw at you today. And you've certainly earned your end of day, and this is the end of my talk. Thank you very much for your attention. Again, if any of this caught your interest, I'm very happy to take questions also by email later on, not just now in the discussion. Okay, thank you very much.